Welcome to our first lesson on the photoelectric effect. We'll be starting off today by taking a look at some of the theory behind the photoelectric effect. Now, the photoelectric effect is the phenomenon in which electrons are ejected from a metal surface when light shines onto the metal. Now, the word phenomenon just means that it's an occurrence. It's something that will happen when, in this case, light shines onto a metal surface and electrons are thus ejected. Now, ejected really means that it will be leaving the metal. Now, we're going to be taking a look at metal. Every metal has obviously electrons inside of it. These electrons are negatively charged. But in order for these electrons to be able to leave the metal, it needs to have a certain amount of energy, or also frequency. Now, when we are going to refer to frequency and energy, they are related to each other. Because, as you'll see in a short while again, energy's formula is capital letter E is equal to H, which you'll see is going to stand for Planck's constant times frequency. So seeing that this is a constant in the middle, it basically means that my energy is proportional to my frequency. So if my frequency would increase, so would my energy. Now, every metal holds these electrons with a certain force, depending obviously on the type of metal. So some of these electrons would need more energy to break free from this force, others would need less. And an indication of this amount of energy or force that the metal holds the electrons with is what we're going to call the work function and the threshold frequency. Let's start off with the work function. The symbol for the work function is going to be a capital letter W, and it's going to have the small zero at the top, which means that it's going to be a constant for a specific metal. Now remember, work is though a form of energy, so we'll be measuring it in joules. Now, the definition for the work function is very important, and you do need to know this off by heart. It's the minimum amount of energy that would be needed to emit an electron from the metal surface. So as now said, every metal has got a specific work function. That means a specific amount of minimum energy needed in order for electrons to be ejected. Now, this work function, just like our formula from previously, can also be calculated if you've got all the specific values, in this case also your threshold frequency. Now, our work function, which will now be in the place of energy, would be equal to Planck's constant times the threshold frequency. Now let's quickly go and take a look as to what is the threshold frequency. Now, threshold frequency is indicated by the symbol F for frequency, small letter, but with a small zero as well at the bottom, which indicate that it's going to be a constant for a specific metal. Now, its definition is very similar to that of the work function, with the only difference now, it's the minimum amount of frequency that would be needed to emit an electron from a metal surface. Our work function was the minimum amount of energy. So just like in the case originally with our energy and our frequency, so our work function and our threshold frequency also go hand in hand. So that means obviously the threshold frequency of a specific metal will be able to go and take that and make use of it to calculate the work function of that specific metal. So when we refer to the minimum amount of energy, we refer to the work function, but we can also refer to the minimum amount of frequency, which indicates the threshold frequency. Now, in order for these electrons to be emitted from this metal, we always say that you need to go and shine a light onto these electrons. So we're going to take a light, and it depends, sometimes you'll see later on the color of the light, whether it is going to be sufficient energy to emit the electron. But we're going to call this piece of light a photon. Now, light travels in packets of energy, which we're going to be calling photons in this case. So this photon is coming in, which means my light, and it's going to hit an electron. Note that it will only hit one electron at a time. It will never hit two electrons. Now, the reason for this being is our photon, once it's going to come in, it will have a specific energy. And we're going to indicate that energy with a capital letter E. And this energy will then be completely transferred to the electron. So if this photon as an example, had 100 joules of energy, it will completely transfer the whole 100 joules of energy to one electron only. And then that electron will have that 100 joules in energy, and the photon will then disappear. Seeing that it has now lost its energy then to this electron, it will then break up. Now, giving its energy to the electron does not necessarily mean that the electron will now be able to leave the metal. It needs to have an energy equal to or greater than the work function of this metal in order to be able to leave. So let's start off here with a work function as an example that this metal has of 80 joules. So that means my photon comes in, it gives it all the 100 joules of energy to this electron. Now this electron, in order to leave, must first pay, in this case it's almost like bail money, the work function before it can leave. So this electron is then basically seen as in jail, and it receives 100 joules of energy, from which it can pay 80 of this joules to the work function, and then he's still left with 20 joules. So because he's got enough energy that is in this case greater than the work function, he will be able to pay the work function and then still leave with 20 joules of energy. Now this energy with which he leaves is going to be seen as his kinetic energy. And remember, kinetic energy has to do with the motion. So depending on how much energy he's got after he has paid the work function, then that energy will be seen as his kinetic energy, and that depends on then on how fast away he'll move away from the metal. Let's take another scenario. If my photon though comes in with only 80 joules of energy, this is only equal to the work function amount. So my electron, once receiving this full 80 joules of energy, will pay the work function, but then it doesn't have any energy left. So that means it will be emitted from the metal, but it will now just be hovering here on top of the metal. It can't go anywhere because it doesn't have this kinetic energy to travel. And let's look lastly at another scenario where our photon now has 60 joules of energy. So it's going to give all of the 60 joules of energy to this one electron, and this electron then notices that it doesn't have enough to pay the work function. So it will still absorb this energy, but because it cannot leave the metal, it will then just distribute and give off this heat energy to the surrounding metal, and that will just increase the temperature of the metal, but in this case the electron can't go anywhere. So when my energy of my photon in this case is greater than the work function, then my electron will be able to leave with a kinetic energy. If my energy though is equal to my work function, then my electron will be able to leave but with no kinetic energy. And if the energy of the photon is then less than the work function, then the electron will not be able to leave. Now we're going to still be making use of our electromagnetic spectrum when we take a look at the photoelectric effect. Now in our electromagnetic spectrum we had an area that had greater wavelengths and then eventually decreased to smaller wavelengths, which also means a higher frequency. Now we started off with radio waves, microwaves, infrared waves, then we had the visible light part, ultraviolet followed after that with X-rays and gamma rays. So as we're going to be moving in this case from left to right, there will be a decrease in my wavelength going to the gamma rays, but an increase in frequency. And remember we said our frequency and our energy is proportional, which means then also an increase in energy. So if I want to make sure though that I will have electrons being emitted from the metal surface, I need to go and pick an energy range here on my electromagnetic spectrum that will actually be able to do so. Now your visible light part though, they obviously start now with red, with the one with the longer wavelength, going over to orange, yellow, green, blue, indigo and violet, which then has a lower wavelength but a greater frequency. So in this case my light, and we're talking about the colors of light that's got the highest frequency, are those ones that is closer to the end of my visible spectrum, and those are the blue, the indigo and the violet type of light. Now you need to have an idea as to what is the order of these lights in your spectrum because many of your questions you'll see a bit later on assumes that you know this and would know which one of them would have the higher energy. And remember as well that your electromagnetic spectrum, that means all of these waves here, will have a specific speed, which we're going to indicate with C, of 3 times 10 to the power of 8 meters per second. So this is the constant for speed of light in a vacuum, or we also use it in air, and it's indicated by a small letter c, and it's 3 times 10 to the power of 8 meters per second. Now it will be given to you though at the back of tests and exams on the constant table. Now light has got 2 natures, one of which is wave nature and the other is a particle nature. Now what we mean about that is that light can act as a wave and sometimes it acts as a particle. So that's how come it's got these 2 natures. Now we do know that it's got a wave nature, as we've seen in our 2 and 3-dimensional wave section, because it can undergo diffraction and interference. Now we'll learn that our light has got a particle nature because of the photoelectric effect, where light will emit electrons from a metal surface. Now we do say in this case that light has got a particle nature because when a photon is shown onto the metal, now we also, just like in all cases when you were still very young, you went and drew the sun with continuous lines pointing outwards, because according to you, light travels in one straight continuous line. But if we were actually able to slow down the speed at which light travels, we would see that it is actually not one continuous line. It's small packets of energy that is traveling, but they travel so fast that we see it as one continuous line. That's how come we call light energy a photon, because it's seen as a packet of energy, which is also sometimes referred to as quanta.